Have you ever wondered what makes something like ChatGPT, well, work? It's not some kind of magic. It's actually an incredibly clever architecture called a transformer. And today, we're going to pull back the curtain on this revolutionary idea and see exactly how it learned to pay attention.
So, let's start with this sentence. As a person, you instantly know that it refers to the animal. Simple, right? But for a computer, this has been a massive hurdle for decades. It's the whole challenge of understanding context. You see, to get this right, the machine has to connect it all the way back to animal while ignoring street. And that ability to find the right context, even across a pretty long sentence, is the exact problem the transformer was designed to solve. It all comes down to learning where to pay attention.
So how did they crack it? Here's our game plan. We'll start with the old, broken way of doing things, then we'll unpack the brilliant idea of attention. After that, we'll see how it gets supercharged, piece together the full transformer recipe, figure out why it totally took over AI, and finally, look at how this idea is being used way beyond just language.
Okay, so before transformers came along, the main tool for handling text was something called a recurrent neural network, or an RNN. The easiest way to think about it is like reading a sentence, one word at a time, and trying to keep a running memory of everything you've seen so far.
But this one word at a time thing had some huge problems. For one, it was really slow, because you couldn't process the 10th word until you dealt with the 9th, and it was terrible at remembering things over long distances. By the time it got to the end of a paragraph, it had probably forgotten what the first word was. All that important context had to be squished into one tiny memory state, which created a massive bottleneck.
And this is where the big breakthrough happened. It's a mechanism called attention. The core idea is just brilliantly simple. Instead of passing a memory down a one-way street, what if we just let every single word look at all the other words all at once to figure out what's important?
This is the key. A word doesn't just have to represent itself anymore. Now it can actively search across the whole sentence. It learns to ask, okay, given who I am, which other words around here will help sharpen my meaning in this specific context?
And this whole search is managed by giving each word 3 different hats to wear. For every single word, we create a query vector, which is basically its question. Then there's a key vector, which is like an advertisement for what it's about. And finally, a value vector, which is the actual information it'll share if it gets picked.
The entire process is captured in this one pretty elegant formula. Now, don't get hung up on the math here. Just think of it as a simple recipe with 4 steps that tells the model exactly how to figure out the importance of every other word. And here's how that recipe works. First, the model takes what it's looking for, the query from the word it, and compares it to what every other word has to offer, their keys. That gives a relevant score. After a quick scaling step, it uses a function called softmax to turn those messy scores into clean percentages. So animal might get, say, a 95% score, while street gets almost 0. Finally, it just blends all the words' values together based on those percentages. And boom, the word it is now infused with the meaning of animal.
So that's the core idea. It's pretty powerful stuff. But the original designers of the transformer added a couple of really clever upgrades to make it even better, because this basic attention mechanism has a couple of blind spots on its own.
First up, a single attention lookup might be a little narrow. So instead of doing it just once, we do it multiple times in parallel. This is called multi-head attention. You could think of it like giving the model multiple sets of eyes. One head might learn to track grammar, another might focus on concepts, and a third might just look at words that are nearby. It just gives the model a much richer view of the text. But there's a bigger problem. The attention mechanism, by itself, is basically like a bag of words. It can see all the words that are there, but it has no clue what order they're in. To it, dog bites man is exactly the same as man bites dog. And as we know, word order is, well, it's everything. The solution here is surprisingly direct. We just add a special vector, a positional encoding, to each word that literally tells the model its position in the sequence. It's kind of like giving each word a timestamp or a serial number, so the model knows, hey, this is the first word, this is the second, this is the third, and so on. Problem solved. All right, so now we have our key ingredients. We've got multi-head attention for finding all sorts of relationships, and we have positional info to understand word order. The final step is to package them all together into a single, repeatable engine block. And here's the recipe for that block. It starts with our multi-head attention layer to mix information across the sentence. Then, a pretty standard neural network chews on each word individually. But crucially, these 2 parts are wrapped with 2 helpers:
residual connections, which act like information highways to make sure the signal doesn't get lost, and layer normalization, which just keeps all the math stable.
So why did this specific recipe end up taking over the entire world of AI? The short answer is that this simple, stackable block design turned out to be unbelievably effective when you scaled it up. I mean, this block is so versatile that just by arranging it in different ways, we get whole families of different models. If you stack them one way, you get encoder-only models like BERT, which are amazing at understanding the full context of a sentence. Arrange them another way, you get decoder-only models like GPT, which are built for generating new text. And if you combine them, you get models for tasks like translation.
But really, the single biggest reason it won is just how incredibly well it scales. By finally getting rid of that one word at a time bottleneck, the whole process could be massively parallelized on modern computer chips. This meant that as we threw more data and more computing power at these models, their performance didn't just get a little better, it absolutely exploded.
And this brings us to the final and maybe most important takeaway. This powerful idea of attention, this learned lookup system, it's not just for words and language. It's actually a general-purpose tool for finding important patterns in almost any kind of data. Take computer vision, for example. A model can chop an image up into a sequence of patches, and then it can use attention to let a patch of a cat's ear attend to a patch of its tail, helping it recognize the whole thing as a cat. The same logic applies pretty much everywhere. It can find patterns across different time steps in an audio file, or discover hidden relationships between columns in a giant spreadsheet. It's even used in models that combine things, like letting a line of text pay attention to specific parts of an image. So at the end of the day, attention is really about one simple thing: giving a machine a powerful way to learn what's important, to find the signal in all the noise. This one idea has completely redefined what's possible with AI. Which leaves us with a pretty big question. As this technology gets even better, what will it learn to pay attention to next?